We're interested in the percentage of houses on the market that are in foreclosure. Now, I'm saying we're interested. You might not care one lick about that, but that's okay. That's okay. That's what we're looking at right now. So, what did I call it? Foreclosure percentages of for sale homes in foreclosure. And we ran a couple intervals together last time. I just want to collect those from you guys really quickly, and then we'll run an interval again for the third one to make sure we remember how to run the command on the machine. Okay, I think we're gonna can't go below 0. We'll just do 2, 4. Stretch it out a smidge more. There we go. Okay, so January 2010. What were the percentages for 2010, friends?
7.1 and 11.4.
7.1 and 11.4. Love it. And here's 7-ish, 7.1-ish to 11.4-ish. So here's January 2010. Actually, I don't want to put it over there. Over here. January 2010. Okay. So tell me again. We have concluded that the 95% confidence interval, which is what this is, 95% confidence interval, is between 7.1% and 11.4%. What does that mean?
We're 95% confident that the foreclosure rate is between 7 and 11.4%.
Perfect. Hey, Stacy. 95% confident that the foreclosure rate is somewhere between 7.4%, 7.1% and 11.4%. Yes, 95% confident. Good. So, can we say it's 8%?
Yes, it could be.
It could be. Can we say with certainty that it's 8%?
No.
Okay. Can we say with certainty that it's 9%?
No.
Can we say anything comparing it to, say, 10% with certainty?
No.
Can we say anything with certainty comparing it to 6%?
Yes.
Can't we now? Can't we now?
Oh, it's certain it's not.
With certainty, it's not that. It's higher than that with 95% certainty. That's where the interval's really shine. Is that if we want to compare it to a parametric value, and I'm not saying the parametric value is meaningful, I just picked that number out of the air because it wasn't in the interval. But suppose, for example, it was known, quote unquote, that the for sale foreclosure rate was 6% in 2004. You can now state with 95% confidence that it's higher. It's at least 1.1 percentage points higher, isn't it? Because at least it's 7.1% with 90, we're all about 95% confidence, which I want to come back to today as well. So basically, if the old foreclosure rate, quote unquote, was say 6%, you can claim that it is now significantly higher. Because 6% is over here, and the 7.1 is over here. But the 7, or excuse me, the 8 and the 9 and the 10, they're all wedged in between. The 11, they're all wedged in between. So therefore, you can't make a call about that. I do this too. This isn't going far enough, is it? Sorry, catch me on that.
Is that 6% though, including its margin of error?
That's the thing.
If they say 6% with a plus or minus.
Can we postpone that question for a moment, Kate? Kate's got an excellent question. Did you hear what it was? The 6% that I just quoted had no margin of error. And I alluded to why it didn't, but I want to come back to that with question number 3 on your quiz, if that's okay. Fantastic question. So if you don't mind me postponing, I think it'll be more applicable in a minute. Thank you. All right, beautiful. How about in 2000? Oh, wait, time out. First thing Stacy said was she's 95% confident that it's between those values. What does that mean?
She's pretty confident. Some of the time it can be not in those.
95% of, I love that, JC. She said 95% of the time. The time of what? 95% of what time? I love that. Thank you. Boom! When you take a random sample of for sale homes, 95% of the time you draw those samples, what are you going to do with your confidence interval? It might not be. That's actually tricky, isn't it now? That's tricky. It might not be between 7.1 and 11.4 the next time. It might be, for example, between 6.9 and 11.7. It might be wider next time. Or it might be a smidge narrower. You might be questioning why it can get narrower with the same sample size. We'll come back to that question too, I promise you. So what is the 95% certainty referring to? I love the fact it's a percentage of time when we draw samples. So we're going to draw a bunch of samples. Say you draw 100 samples. of the same sample size, from the same population. 95 out of those 100 intervals are going to do what? Say that again, Kate.
Their averages are gonna fall between a 7.
And what very special average are you talking
The
about?
averages of the
Say it in a more simple way. Yes, that's correct. But say it in a more what are you trying to estimate?
P samples of population.
Yes, yes. Little p, which is the population's proportion. See, what we're interested in knowing is what percentage of houses out there for sale are in foreclosure. Are you ever going to know that? No, you can't. It's too big, right? So what you do is you draw this interval. And you're 95% confident that that value is in the interval. So somewhere between the low end and the high end. Now the kicker with that is what the 95% actually means. It doesn't mean there's a 95% chance it's in this one. Okay? It doesn't mean there's a 95% chance it's in this one. It either is or it isn't. It means if you draw repeated ones, 95% of those are going to contain what you're looking for. So, you can think of it if you want either of those two ways. Some of you are looking at me like, wait a minute, you said the same thing twice, 2 different ways. Actually, I did, believe it or not. If you repeatedly draw intervals, like we did with the penny spins. Remember how those penny spin intervals kept going side to side and side to side, and most of them didn't have 50%, but a few of them did? Over time, I can't wait to do this, hundreds more times, because I'm going to be here that long, probably. And I'm going to have all these beautiful intervals where I see 95% of them not containing 0.5. And then the other 5% might, because it's a function of probability. We're going to go.
But there's a minimum.
So what's the minimum?
Well, isn't there a minimum number of samples that you have to draw to get?
Hold that. You asked that awesome question last time. I know you did, and I thank you for that. She asked the minimum number of samples we have to draw. For example, a minimum sample size, I think is what you're getting at, right? Good. If you don't mind, I want to wrap this up before we get into that, because that's a fantastic question. Yes, there is what I call a bare minimum sample size. I'm going to tell you what it is. It's 10. And you'll see why momentarily. But there's a way, you'd be insane to accept 10 as a sample size, because your margin of error is so wide that it's essentially useless. Great question. I just want to kind of wrap this up first. Awesome, awesome question. How about in 2013, it was April 2013,
8 and 10.8.
8 to 10.8. Thank you. I want to take this out of here. Thank you guys for the interpretation of 95% confidence. It's very nice. 8 to 10.8. 8 to 10.8. Coming out to here-ish. This is April 2013. And I think this is the last thing I asked you guys last time. How are those intervals similar? Oh, good, they overlap. I love that.
Well, they look like they're the same minimum.
Boom. Very nice, Dan. They definitely have essentially the same middle percent. Middle. I just changed middle to middle. Middle percentage. In other words, p hat is essentially the same in both. I think it was like 9.3 and 9.3 or 9.26 and 9.3. I forgot now what it is.
9.2 and 9.4.
Thank you. 9.2, 9.4. Now, the news media, you know what they're going to say, of course. Is this a 9.2 and that's a 9.4?
It's a huge difference.
They're going to say, for sale percentages of foreclosure houses jumped in April from 2010 to 2013, from 9.2% to 9.4%. And 9.4 is a bigger number than 9.2. But when they say that, what are they mistaking? The 9.4 and the 9.2 for? That came out right.
The absolute.
Use a different word besides absolute. I love that. You're right.
Population.
Yes, they're looking for they're calling 9.2 and 9.4 the parameter values, not the sample values. Now, when you said who said average of averages earlier? That was a wonderful statement. Somebody said that average. Kate, when you said average of averages, that is the same as the parameter value. But in order for the news media to report average of averages, in other words, the P double hat, the hat of all the P hats, if you will, they'd have to draw every single possible sample from the population. Well, that's stupid. Why would you do that? If you can draw every single sample from the population, just draw the damn population. But you can't. That's why you have to slap errors on your estimates. You have to increase your confidence. If you only report P hat, you're at 0% confidence. Because what's the chance that you literally exactly caught the same thing? Exactly. Sherry's like, if you didn't, exactly, it's 0% confident. The wider this bad boy gets, the more confident. Some other stuff happens too, which we'll get into in this course. So, good. These are the same, essentially, because they have the same center. How are they different? How are they different? Oh.
Standard deviation's different.
Good! May I call it standard error? And if you call it, JC asked this question last time, it was a great question. Call it standard deviation if you want, I have no problem with that. I'm going to try to refer to it as standard error only because you guys that are moving into the research fields are going to constantly see things like sum of squares, standard error, these terms pop up. The difference is minor but important. Standard deviation is the actual deviation of a set sample. Whereas a standard deviation, or a standard error, excuse me, is how you apply that to be inferential when you try to apply it to more than one. So a standard deviation, if you will, is essentially like a fixed number tied to one sample. Where a standard error can then take that sample and say, okay, we're going to predict something with this. That's where the central limit theorem kicks in, the root n in the denominator. That's what the adjustment, that's the beautiful part of it. All it takes is a root n in the denominator to take care of that. Mathematically awesome. So, why did the standard error go down? Because sample size increased. I don't expect you to have this formula at your beck and call, but the standard error for this confidence interval is equal to radical p hat q hat over n. That's how you calculate one standard error, and then you multiply it by however many critical values you need to develop the confidence that you want. Now when I say you do this, we did it once, and we will never do it again for these, because the TI will now take care of it for us. But that's what's going on behind the scenes, just so you know, which is like the penny spin experiment, exactly the same. We called this 2, we put a 2 out here, right? We called that a margin of error, and we called that 2, and we put our p hat and q hat values in, and we divided by our sample size of 310, I think it was, for our pennies. But the big thing to focus on is that standard error. And because n is in your denominator, the larger your sample gets, the skinnier your interval is going to get as a result. Also, while we're looking at this formula, I don't want to spend too much time looking at the formula because it tends to give people highs. This is also why your standard error can change even with the same sample size. So for example, if I drew, how many did we draw on that first sample? Do you guys remember? 702. If we drew 702 again, it's possible that the standard error wouldn't be exactly the same. So what I'm telling you, Sherry's like, wait a minute, that's crap. Because it's the same formula being used, right? So what I'm saying is, if I draw a sample of 702, and that standard error is going to be p hat q hat over 702, right? 702, that's sample size 702. And if I draw a second, this is the first one, and this is the second one of sample size of 702, which is also going to have standard error of p hat q hat over 702. I'm sitting here today telling you they might be different. How dare I? But why could they be? Because the p hat could be different for each one, right? Remember what we said. 95% confidence means out of all the intervals you have created, 95% of them are going to catch the true little p value. That doesn't mean p hat's going to be exactly the same each time. We just saw it happen twice, it got different. It went from 2.7, whatever the hell Dawn just said, 9.2 to 9.4, right? If that's 9.2, I know I'm changing the sample sizes to fit my argument here, but if that's 9.2% and that's 9.4%, these are going to be a little bit different, aren't they? Not magnificently different, but a little bit different, a teeny bit different. So just, the margins of error can change as your samples change, even if the sample size stays the same.
But for the most part, it's going to catch the same.
Catching still happens 95%, thank you. The idea of catching still happens at 95%, Kate. Yes, absolutely. Good question, good question. Say that again?
So it doesn't really matter.
Well, I wanted to make sure that you guys, I saw a couple weird looks when I said this can change. This can change as the sample size stays the same. Someone was like, I want to make sure that everybody understood why. Mathematically, that's why. So, but yes, essentially the catching percentage happens exactly at the same time. You can also see how, depending on the size of little p and little q, these can get more extreme or less, more extreme as in more wide or less, let's not use the word extreme, wider or narrower. For example, if p and q are very close to a half, 0.5, because they're complementary, right? They have to add up to 100%. So if that's 0.5 and that's 0.5, then the product of that is 0.25, right? But in our example right now, this was like 0.1, 0.09. I'm going to call it 0.1 to make the math easier. That's 0.1. That means Q would be 0.9. So the product of both would be 0.09, which is vastly different than 0.25, which would make the margin of error actually much smaller, even for a sample size of 702, it would make it whatever that is, twice or something as narrow. That's a function of the binomial. The binomial standard deviation is dependent upon its center, just like an average is, just like x bar is. But it's kind of exaggerated in this case. So that's the mathematics. Don't get too hung up on the math. That's the mathematics behind it, what's going on. Fair? Good. All right, let's get this formula off the board. It's making you all sick. It's interesting. It's very interesting. Oh, don't take the formula away.
I like formula.
Well, that's okay. There's just too many of them to keep track of. I mean, that's the thing. That's why I like the machine. I like when you see the formulas. I like how you know how they work. But it's just too easy to screw them up when you're working. I mean, that's why we have things like Excel and the TIs and things. I'm convinced. All right, let's answer the last question on a quiz then.